Hello there, and welcome to the Sleepy Science. I am so glad you found your way here. As the quiet darkness gathers around you, take a moment to settle in. You've got nothing to do but rest. Let your mind relax, your breathing slow, and your body grow light as if gravity itself has softened, releasing its gentle hold. Feel yourself becoming lighter, softer, floating. If these calm, curious explorations help you unwind or give you a quiet way to end your day, consider liking and subscribing to the channel. It helps others find their way here too. Tonight, we aren't simply looking outward at the grand, spinning galaxies or the deep, dark expanse of space. Tonight, we are turning our gaze inward, plunging into a universe hidden from our naked eye, a realm of constant motion and profound mystery. We are entering the secret world of the atom, a place where reality itself is woven from invisible threads, where particles dance and light whispers of unseen truths. We'll drift through 100 quiet truths of this atomic world, uncovering the fundamental secrets of everything you touch, everything you feel, everything you are. So, let your thoughts gently untangle and allow your mind to wander through the minuscule landscapes we're about to explore. Rest softly. Long, long ago, beneath the silent gaze of a starlit Grecian sky, human minds began to dream of what lies beneath the surface of all things. Imagine, if you will, the gentle hum of cicadas in the warm night air, the scent of olive trees, and the soft flicker of oil lamps illuminating parchment scrolls. This was a time before telescopes could reveal distant nebulae, before microscopes could unveil hidden microbes. It was a time when the greatest tool for understanding the universe was pure thought, spun patiently from curiosity and wonder. It was here, in this quiet contemplation, that a philosopher named Democritus began to ask a truly revolutionary question. He looked at a smooth stone, or a flowing stream, or a breath of air, and he wondered, what if you were to cut it in half, and then in half again, and again and again? Would you eventually reach a point where it could no longer be divided? A point of fundamental, unbreakable essence. His brilliant mind, without the aid of any instrument, conceived of tiny, invisible, and utterly indivisible particles. He called them suni atomostai, a Greek word that simply means uncuttable or indivisible. Envision these ancient atoms now in your mind's eye, not as shimmering spheres or complex structures, but as pure, elemental building blocks. Democritus believed they were eternal and unchangeable, existing in an infinite void, constantly moving, colliding, and combining in countless ways to form everything we perceive. Imagine the vast, empty space, a quiet ocean, where these tiny, silent specks drift and gently bump into each other, forming mountains and rivers, trees and living creatures, even the very air you breathe. Each atom, a small, quiet truth, contributing to the grand, intricate tapestry of existence. This was a world woven purely from thought, a tapestry spun from logic and intuition alone. You can almost feel the weight of this ancient wisdom, the profound simplicity of an idea that, in its essence, echoes through millennia. For centuries, this profound whisper about atoms faded, overshadowed by other philosophies that held sway. The concept of indivisible particles seemed too abstract, too far removed from our immediate senses. But the truth, like a persistent current beneath a still lake, never truly vanishes. Then, much, much later, as the light of scientific inquiry began to brighten, A quiet English schoolteacher named John Dalton dusted off these ancient ideas. He wasn't just pondering abstractly. He was observing, measuring, experimenting with gases. He noticed that elements always combine in fixed, simple ratios, as if they were made of distinct, unchangeable units. Imagine him in his laboratory, a man of meticulous observation, meticulously weighing gases, charting his results, and seeing patterns emerge like constellations in the night sky. Dalton, drawing on the spirit of Democritus, proposed that each element is indeed composed of its own unique type of atom. All atoms of a given element, he suggested, are identical in mass and properties, and they cannot be created, destroyed, or subdivided in chemical reactions. He gave the atom a new scientific life, transforming it from a philosophical speculation into the cornerstone of modern chemistry. He laid the quiet, sturdy foundation upon which all subsequent understanding of matter would slowly, patiently be built. So, close your eyes and picture these early atoms, simple, solid, unyielding, the foundational bricks of the universe quietly awaiting the many astonishing discoveries that would soon reveal their hidden complexities. As the 19th century gently yielded to the 20th, the scientific world, much like a sleepy child stirring awake, began to peer more closely into the atom's veiled interior. The idea of the atom as a simple, indivisible sphere, solid and uniform, was about to be challenged, not by philosophy, but by the quiet hum and subtle glow of new experimental wonders. This was the era of discovery, when unseen forces began to whisper their secrets through glass tubes and flickering sparks. Imagine a darkened laboratory, lit only by the soft, ethereal glow of a cathode ray tube. This wasn't a magic trick. It was the cutting edge of science. Scientists were observing mysterious rays emanating from a negatively charged electrode, traveling through a vacuum. These cathode rays were invisible, yet they made the glass tube fluoresce with a gentle, otherworldly light. They could even make a small paddle wheel spin, hinting at their particulate nature, yet no one knew exactly what they were. Enter J.J. Thomson, a brilliant and methodical physicist working at the Cavendish Laboratory in England. He devised elegant experiments to understand these mysterious rays. Imagine him carefully adjusting magnetic fields and electric plates around the cathode ray tube, watching as the glowing beam bent and curved, like a silent, invisible current being steered by unseen hands. Through these meticulous observations, Thomson made a truly astonishing discovery. The cathode rays were not just energy. They were composed of tiny, negatively charged particles. And these particles, he realized, were far, far smaller than the smallest known atom. This was a profound moment, a quiet gasp in the scientific community. The atom, once thought to be the fundamental, indivisible unit, now revealed itself to have 2 feet part 2. It was no longer a solid, impenetrable sphere. These tiny, negatively charged particles were eventually named electrons. The world had, for the first time, seen something smaller than an atom. With this new piece of the puzzle, Thomson needed to update the model of the atom. If there were negatively charged electrons, and atoms themselves were known to be electrically neutral, then there must also be an equal amount of positive charge somewhere within the atom to balance it out. And so, with a gentle, imaginative leap, he proposed his famous plum pudding model. Picture it in your mind, a comforting image much like a sweet, soft dessert. The atom, according to Thomson, was a sphere of uniformly distributed positive charge, like a fluffy, positive cake or pudding, and scattered throughout this positive dough like delicious raisins or plums, or the tiny negatively charged electrons. Imagine these electrons nestled gently within the positive mass, quietly holding their places, creating a harmonious balance of charge. This model was, for its time, revolutionary. It painted a picture of an atom with internal structure, a miniature universe with its own inner workings. It was a gentle, inviting vision, easy to understand and visualize. It explained how electrons could be emitted from atoms, as in cathode rays, and why atoms were generally neutral. While its reign was relatively brief, quickly superseded by further discoveries, the plum pudding model served as an essential stepping stone. It softened the scientific mind to the idea that the atom was not the end of the line, but merely the tranquil threshold to an even more astonishing, complex, and unseen world within. It was a sweet, conceptual dessert that nourished the curiosity and paved the way for even deeper insights. The cozy, comforting plum pudding model, with its electrons nestled gently in a positive dough, seemed like a perfectly reasonable picture of the atom. It was elegant, simple, and accounted for the newly discovered electron. But in science, even the most beautiful theories must stand the test of observation. And sometimes the most astonishing truths are revealed not by what you expect to see, but by what utterly surprises you. Imagine, if you will, the quiet laboratories of Ernest Rutherford, a former student of J.J. Thomson, who in the early 20th century was pursuing even deeper mysteries of the atom. He was known for his direct, almost fearless approach to experimentation. His team devised a groundbreaking experiment, one that would utterly shatter the prevailing view of the atom and reshape our understanding of matter. Picture the scene: a small lead box containing a radioactive source, gently emitting a stream of tiny positively charged particles, known as alpha particles. Think of these alpha particles as microscopic energetic bullets, quietly yet swiftly leaving their source. These bullets were then directed towards an incredibly thin sheet of gold, foil thin, so thin, in fact, that it was only a few hundred atoms thick. Imagine it as a shimmering, almost translucent veil of gold, delicate as a whispered thought. Surrounding this gold foil was a fluorescent screen, designed to flash with a tiny sparkle of light whenever an alpha particle struck it, marking its path. According to Thomson's plum pudding model, the alpha particles, being much heavier and more energetic than electrons, should have passed straight through the flimsy gold atoms with only very minor deflections. After all, the positive charge in the plum pudding was spread out, diffuse, and wouldn't offer much resistance to a fast-moving projectile. You'd expect them to drift through, perhaps wobbling slightly, like tiny pebbles skimming across a soft, uniform jelly. But what Rutherford's team observed was anything but expected. Most of the alpha particles did indeed pass straight through the gold foil, creating quiet flashes on the screen behind it, just as predicted. But then, to their utter astonishment, a small number of particles, perhaps one in every 8,000, were deflected at very large angles. And even more incredibly, a tiny fraction of them, perhaps one in every 20,000, actually bounced tuna straight back towards the source. Rutherford famously described this phenomenon with a vivid analogy that still resonates today. He said it was about as incredible as if you had fired a 15-inch shell at a piece of tissue paper and it came back and hit you. Imagine that sense of profound shock of an utterly impossible event unfolding right before your eyes. The very foundations of what they thought they knew about atoms trembled. This meant the plum pudding model was fundamentally wrong. For an alpha particle to be deflected so sharply, or to bounce back, it had to have encountered something incredibly dense and positively charged, concentrated in a very tiny space within the atom. It couldn't be spread out like a pudding. It had to be a powerful microscopic core. And so, Rutherford, with a bold stroke of insight, proposed a new model. The atom, he declared, consists mostly of empty space. At its very center lies a tiny, dense, positively charged nucleus, containing almost all of the atom's mass. The electrons, those tiny negative whispers, then orbited this nucleus in the vast, empty region surrounding it, much like planets circling a distant sun. Think about that for a moment. You are touching your skin, feeling the quiet solidity of your hand. You are resting on a bed, feeling its firm support. Yet, at the atomic level, nearly everything is empty space. The alpha particles that passed straight through the gold foil weren't passing through solid gold. They were passing through the vast, empty regions within the gold atoms. Only when an alpha particle happened to strike, or come very close to, the minuscule dense nucleus was it repelled with enough force to deflect or bounce back. This revelation was profound. It told us that the solidity of matter, the very substance of our world, is not about atoms physically touching each other like billiard balls. Instead, it is about the powerful electrical forces of repulsion between the positively charged nuclei and the negatively charged electron clouds of neighboring atoms. It is the silent, unseen ballet of electromagnetic fields that gives things their apparent firmness, their resistance. So, as you rest, consider this amazing truth. The chair you sit on, the floor beneath your feet, even your own body. For they are all, at their core, mostly empty space. A vast, quiet emptiness, punctuated by tiny, dense nuclei and swiftly moving electrons, creating an illusion of solid form through the dance of unseen forces. The atom was no longer a simple sphere. It was a miniature solar system, a vast void with a powerful heart, revealing a world far more empty, yet far more wondrous than anyone had ever imagined. And so, we find ourselves drifting from the startling emptiness that Ernest Rutherford revealed within the atom. You've journeyed through a space that was once thought to be solid, only to discover it was almost entirely vast and open, with a tiny, dense nucleus at its heart. But this revelation brought with it a quiet puzzle. If electrons, those tiny negative charges, were orbiting this positive nucleus like planets around a sun, why didn't they spiral inwards, drawn by the irresistible electrical pull, eventually collapsing the atom into nothingness? Classical physics, with its elegant equations, predicted such a collapse, a fleeting existence for every atom. But here we are, in a world built of stable, enduring matter. It was into this gentle mystery that Niels Bohr stepped, offering a profound insight that began to weave the first threads of quantum theory into our understanding of the atomic world. He proposed that electrons didn't just orbit anywhere, willy-nilly, like a cloud of cosmic dust. Instead, they were confined to very specific, quantized orbits, like invisible, concentric shells around the nucleus. Imagine, if you will, a staircase leading up into the vastness of an atomic sky. An electron can only rest on one of these steps. It cannot linger in between. Each step represents a distinct energy level, a precise quantum of energy that the electron possesses. This was a revolutionary thought, a quiet whisper that defied the continuous nature of the classical world. It suggested that energy itself was parceled out in discrete packets, not an infinitely divisible quantity. And within these special orbits, Bohr suggested an electron would simply persist. It would not radiate energy. It would not spiral inward. It would simply continue its gentle journey, a tiny world spinning silently within its designated path. It's as if the atom held a secret pact, a gentle agreement with its electrons. Stay here, and you are safe. But what happens when an electron wants to move? It doesn't glide smoothly from one orbit to another. Instead, it makes a sudden instantaneous leap, a quantum jump from one step to another, without ever truly occupying the space in between. If an electron absorbs a tiny packet of energy, a photon of light, it can leap to a higher, more energetic orbit, further from the nucleus. It's like a tiny dancer, absorbing a surge of energy and twirling gracefully to a new, outer ring. And when that electron falls back to a lower orbit, to a step closer to the nucleus, it must release that absorbed energy. It does so by emitting its own tiny packet of light, its own photon, with an energy precisely matching the difference between the two orbits. This is not a chaotic burst, but a delicate, precise release, a specific whisper of light. And because each element has its own unique arrangement of electron orbits, its own particular atomic staircase, each element emits and absorbs light at very specific characteristic wavelengths or colors. You can imagine these distinct colors as the unique fingerprint of an atom, its individual song in the cosmic symphony. If you've ever gazed at the mesmerizing burst of colors in a firework display, you've witnessed this atomic dance in action. Vibrant reds, blues, and greens are not simply random light. They are the collective whispers of electrons within different metal atoms. Strontium for red, copper for blue, barium for green, as they leap to higher orbits in the heat of the explosion and then gracefully fall back, each releasing its characteristic color, painting the night sky with quantum art. This planetary model, with its fixed orbits and quantum leaps, brought a beautiful order to the previously chaotic internal life of the atom. It explained the stability of matter, the discrete nature of light, and the exquisite precision of atomic spectra, solving mysteries that had long troubled the scientific mind. It was a model of quiet elegance and harmony, a miniature cosmos where tiny celestial bodies followed their preordained paths, exchanging energy with the universe in a ballet of light and shadow. While later discoveries would reveal an even more complex and fuzzy reality within the atom, Bohr's model was a crucial illuminating step, a gentle guide leading us deeper into the heart of matter, showing us that even at the smallest scales there is a profound underlying structure, a quiet rhythm that keeps the universe in motion. It prepared us for an even stranger journey, into a world where familiar concepts of particles and waves would begin to gently blur and intertwine. The gentle harmony of Bohr's planetary model, with its electrons elegantly confined to specific, quantifiable orbits, offered a comforting picture of the atom. It was a step on our journey, a moment of beautiful clarity. But as we continue to drift deeper into the heart of the microcosmos, we encounter a reality far more elusive, far more dreamlike, where the lines between what we perceive as solid and what we understand as ephemeral begin to gently dissolve. Imagine, if you will, the soft shimmer of light on water, a ripple moving across a still pond. Light, for centuries, was understood to be a wave, flowing and spreading, creating patterns of interference just like those ripples. But then, as our instruments became more sensitive, as our understanding deepened, it began to whisper another secret. Light also seemed to arrive in tiny discrete packets, like perfectly formed droplets of energy, which we now call photons. It was as if light held a dual nature, a quiet contradiction within its very being, sometimes a flowing wave, sometimes a discrete particle. This profound duality, this ability to be both wave and particle, is one of the most astonishing truths of the quantum world, and it extends far beyond light. It touches everything, even the most fundamental building blocks of matter. To truly glimpse this, let us gently revisit a famous experiment, one that has captivated and puzzled scientists for over a century: the double-slit experiment. Picture a screen with two very narrow, parallel slits cut into it. If you shine a light, a stream of photons, through these slits onto a second screen behind them, you don't just see two bright lines. Instead, you see a pattern of alternating bright and dark bands, an interference pattern. This is precisely what you would expect if light were a wave, with the ripples from each slit overlapping, and either reinforcing or canceling each other out. It is the wave nature of light softly announcing its presence. Now, imagine doing this with particles, with something you might intuitively think of as a solid, distinct entity, like electrons. If you fire a stream of electrons, one by one, through those same two slits, what would you expect? You might anticipate two lines, corresponding to the electrons passing through either the left or the right slit, just like firing tiny bullets. But what unfolds is far more intriguing, far more enchanting. Even when electrons are sent through one at a time, so that each electron has no other electron to interact with, a gentle interference pattern slowly begins to build up on the detector screen. How can a single electron, a tiny particle, create an interference pattern? For that to happen, it must, in some sense, be passing through both slits at once, interfering with itself, like a ghostly ripple spreading out and passing through both openings simultaneously. It's as if the electron doesn't choose a path until it absolutely has to, instead existing as a shimmering cloud of possibilities, a gentle wave of potential spread across space. This is the heart of wave-particle duality. Every particle, every electron, every atom, even you in theory, exists not as a definite point, but as a probability wave, a collection of all possible locations and states. It's a hazy, dreamlike existence, a gentle mist of potential, until something happens, and that something is observation. When you try to observe which slit the electron goes through, when you place a detector near one of the slits to gently peek at its path, the interference pattern vanishes. The electron suddenly, decisively, behaves like a particle, choosing one slit or the other. It's as if the act of looking, the very act of measurement, gently forces the electron to make a choice, to collapse its wave function from a spectrum of possibilities into a single definite reality. This is not a flaw in our instruments or a limitation of our technology. It is a fundamental truth of the universe at its smallest scales. The world, in its deepest essence, is not a collection of fixed, solid objects simply waiting to be discovered. It is a dynamic, shimmering interplay between potential and reality, a gentle dance between what could be and what is. Before you observe it, before you shine your gentle light upon it, an electron is not definitively here or there. It is everywhere at once. A quiet hum of probability, a whisper of countless possibilities, and the very act of reaching out, of asking a question, gently brings it into definite being. It's a profound thought to ponder as you drift into slumber. The universe, in a very real sense, might be waiting for your gentle gaze to take its form. As the concept of wave-particle duality settles gently in your mind, like a soft blanket of quantum fog, we find ourselves at another profound threshold, a place where the very act of knowing becomes intertwined with the nature of reality itself. This is the domain of Werner Heisenberg and his famed uncertainty principle, a gentle cosmic whisper that tells us there are fundamental limits to what we can ever truly know about the quantum world, not because our tools are insufficient, but because the universe at its smallest scale embraces an inherent, beautiful fuzziness. Imagine trying to describe a dream as it unfolds. The more you try to pin down one detail, the color of a fading flower, the exact words spoken by a fleeting figure, the more another aspect of the dream seems to slip away, to blur at the edges. The uncertainty principle suggests something similar, but far more fundamental, about the universe's tiny constituents. It states that you can never simultaneously know, with perfect precision, both the exact position for the undo, the exact position for the undo, the exact momentum, which is the measure of its speed and direction, of a quantum particle. This is not simply a limitation of our ability to measure. It is not that we just need better microscopes or more sensitive sensors. No, this is a deep intrinsic property of nature itself, a fundamental rule woven into the very fabric of reality. The universe, in its quiet wisdom, will not allow us to have both pieces of information with absolute clarity at the same time. If you try to precisely pinpoint the position of an electron, say by shining a very short wavelength of light on it, which carries a lot of energy, that very act of observation will impart energy to the electron, changing its momentum in an unpredictable way. It's like gently tapping a dandelion seed with a feather to see where it is. The feather's touch, however soft, will inevitably send the seed drifting off in a new direction. You will know where it to meet was, but its momentum has become uncertain. Conversely, if you try to measure its momentum with great precision, perhaps by gently letting it drift through a very long, undisturbed path, then its exact position becomes smeared out, a long shimmering wave of probability. You know its speed and direction with exquisite accuracy, but its precise location at any given moment becomes wonderfully indefinite. It's a delicate cosmic dance, a trade-off that the universe quietly insists upon. The more certain you are about one, the less certain you must become about the other. This inherent uncertainty lends a philosophical depth to our understanding of existence. It whispers that the world, at its most fundamental level, is not a perfectly deterministic clockwork mechanism, where every cause leads to an entirely predictable effect. Instead, there is a gentle, irreducible element of chance, of probability woven into the quantum fabric. This fuzziness isn't a bug in the cosmic code, it is a feature. It suggests a universe that is alive with possibilities, where true randomness can emerge from the very heart of matter. You can find a quiet beauty in this uncertainty. It reminds us that our observation, our gentle inquiry, is never a neutral act. We are not detached observers of a static reality. We are participants, gently nudging the universe into one state or another, simply by asking a question. The act of knowing changes what is known. This principle doesn't breed chaos. Rather, it introduces a profound, almost poetic humility into our scientific endeavors. It teaches us that the universe holds some secrets so tightly that it will not reveal them both at once, choosing instead to present a beautiful, intricate balance between clarity and mystery. So, as you rest, let the gentle embrace of uncertainty wash over you. It is a reminder that there is always more to the universe than meets the eye, a deeper layer of existence that resists perfect definition, yet holds an undeniable quiet truth. It is a universe that breathes with paradox, where the known and the unknown exist in a delicate, harmonious balance, a soft space where exactness yields to the shimmering beauty of probability. When we speak of the quantum realm, the very fabric of reality seems to shimmer with an enchanting uncertainty, challenging everything our senses tell us about the world. And nowhere is this more beautifully, or perhaps unsettlingly, illustrated than in the famous thought experiment of Schrodinger's cat. Imagine, if you will, a sealed box, a silent enclosed universe. Within this box, a single, delicate cat rests. Alongside our feline companion, there is a tiny, meticulously arranged device. At its heart lies a single radioactive atom. This atom, through the whimsical, unpredictable dance of the quantum, has an equal probability of either decaying or remaining stable over a specific period of time. First, exactly an hour. If the atom decays, a detector registers this event, triggering a hammer to fall. This hammer shatters a small vial of poison, releasing its lethal contents into the sealed air. But if the atom remains stable, the hammer stays still, the vial unbroken, the air pure, and our cat continues to slumber peacefully. The crux of the mystery lies in the very nature of that radioactive atom. In the strange and ethereal world of quantum mechanics, before any observation takes place, that atom is not simply decayed or undecayed. It exists in a peculiar, ghostly state, a superposition, where it is both possibilities at once. It is both decayed and sundi not when decayed, simultaneously, like a whisper echoing through two chambers at once. Because the cat's fate is inextricably linked to this tiny quantum event, the cat itself, before the box is opened and an observation made, is also said to exist in a superposition. It is, in a profound and unsettling quantum sense, simultaneously both alive and dead. Not merely a guessing game of whether it is one or the other, but truly a blend of both states, a shimmering, uncertain existence within the darkened confines of its temporary home. It isn't until you, the observer, gently, perhaps even hesitantly, open that box that the quantum uncertainty collapses. At that precise moment of interaction, the universe makes its choice, and the cat assumes a definite state, either peacefully breathing or tragically gone. This thought experiment, conceived not to be taken literally, but to highlight the baffling implications of quantum mechanics when scaled up to our everyday world, invites us to ponder the very nature of reality itself. What does it mean for something to exist in multiple states at once? And what role does our act of observation, of becoming aware, play in solidifying that reality? It's a question that gently nudges the boundaries of our understanding, inviting a quiet, meditative wonder. The cat, in its quantum slumber, becomes a profound metaphor for the deep hidden layers of existence that precede our perception. This concept of superposition, while challenging to our classical minds, isn't just a philosophical curiosity. It is the very foundation of emerging technologies like quantum computing, where tiny quantum bits, or qubits, can exist in a superposition of 0 and 1 simultaneously. This allows them to process vast amounts of information in parallel, unlocking computational powers beyond our current comprehension. And some theories even suggest that this quantum splitting of possibilities might hint at the existence of a grander, ever-branching multiverse, where every quantum choice made by the universe leads to the unfolding of a new, parallel reality. As you rest and drift, consider the quiet cat in its box, simultaneously breathing and still, a tiny, poignant mirror reflecting the grand, unseen dance of all existence. Asterisk, asterisk, asterisk. Now, let us turn our gaze to another astonishing quantum phenomenon, one that seems to defy the very laws of common sense, yet is constantly at play, shaping the stars above and the technology within your grasp. Imagine a sturdy wall, solid and unyielding. In our everyday world, if you don't have enough energy to climb over it, you simply cannot pass. The wall acts as an absolute barrier. But in the ephemeral, probabilistic world of the quantum, particles sometimes perform what can only be described as a magic trick. They simply pass through such a barrier even without the classical energy to surmount it. This is the curious, improbable dance known as quantum tunneling. Consider a tiny electron, an almost infinitesimally small whisper of energy. It approaches an energy barrier, a wall of force that, by all classical reasoning, it should not be able to cross. Yet every now and then, as if by an unseen gentle hand, the electron simply appears on the other side. It doesn't bore a hole, nor does it leap over. It momentarily ceases to be on one side and then, with a silent, graceful shift, reappears on the other. It is as if a fleeting, secret doorway opens and closes in the fabric of space, allowing this tiny traveler to pass. This isn't a flaw in our understanding. It's a fundamental probabilistic aspect of how the universe truly works at its smallest scales. The particle's wave, like nature, allows its probability wave to extend, however faintly, into and through the barrier, giving it a small but very real chance of existing on the other side. This seemingly impossible feat, this ghost-like passage, is not merely a theoretical oddity. It is a quiet, constant force driving some of the most fundamental processes in the cosmos and underpinning much of our modern technology. Look up at the stars or consider the gentle warmth of our own sun. Deep within their fiery hearts, light atomic nuclei, primarily hydrogen, are trying to fuse together to form heavier elements like helium, releasing immense amounts of energy in the process. However, these nuclei, being positively charged, naturally repel each other. They need enormous energy to overcome this electrostatic repulsion, a barrier that, by classical physics, the sun's core isn't quite hot enough to consistently surmount. But here, quantum tunneling steps in, a silent hero. A small fraction of these nuclei, despite not having enough classical energy to fully overcome the repulsive barrier, can tunnel through it, embracing their partner to fuse. This improbable dance, occurring trillions upon trillions of times every second, is the quiet engine that powers the sun and all the stars, bathing our world in light and warmth, and literally keeping life alive. Without quantum tunneling, the sun would not shine, and the universe as we know it would be a cold, dark, and utterly different place. And this quantum magic isn't confined to the distant stellar furnaces. It is at work in the very devices that permeate our modern lives. The flash memory in your phone, tablet, or computer, which quietly stores all your digital memories and information, relies on quantum tunneling. Tiny electrons tunnel through thin insulating layers to get trapped in specific areas, representing the ones and zeros of digital data. This subtle, silent passage of electrons allows your device to remember, to record, and to play back the stories of your life. Even certain types of microscopy, like the scanning tunneling microscope, utilize this effect to create incredibly detailed images of individual atoms, gently probing the surface of materials by feeling the tunneling currents of electrons. So, as you drift into slumber, consider the invisible, silent doorways being opened and closed, the quiet magic of particles passing through walls, a constant, improbable dance that illuminates the stars and weaves the tapestry of our technological world. Asterisk, 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 having journeyed through the ethereal dance of electrons and the curious laws of the quantum, let us now gently pull back the veil even further and venture into the very heart of the atom, its nucleus. This tiny, incredibly dense core is where almost all of the atom's mass resides, a bustling, vibrant heart that defines its very essence. And within this powerful, compact space, two fundamental particles reside, two quiet guardians shaping the identity and stability of every element in the universe, the proton and the neutron. Imagine, if you will, the nucleus as a miniature, incredibly vibrant city. Its primary residents are the protons, each one carrying a single, positive electric charge. These are the particles that truly define an element. Every atom of hydrogen, for instance, always carries just one proton. Every atom of carbon, the building block of life, always has 6 protons. And every atom of oxygen, the very breath of our world, contains 8 protons. The number of protons is the atom's unique identity card, its atomic number, a fundamental quantity that dictates its place in the grand periodic table of elements. The early whispers of their discovery came from experiments with gas discharge tubes, where scientists observed positively charged rays, slowly revealing the existence of these fundamental positive carriers. Alongside the protons, nestled intimately within the nucleus, are the neutrons. These are the quieter, neutral companions, carrying no electric charge, yet possessing almost the same mass as their proton counterparts. The discovery of the neutron came much later, in the early 1930s, a testament to its elusive chargeless nature. Because it carries no charge, it does not interact with electric fields, making it far more challenging to detect than its positively charged sibling. Yet, its presence is profoundly important. The neutrons act like a stabilizing glue within the nucleus, helping to counterbalance the fierce electrostatic repulsion between the positively charged protons, which would otherwise drive the tiny nucleus apart. They are the silent balancers, the unseen anchors, holding the atomic family together. Think of protons and neutrons as the yin and yang of the atomic heart, or perhaps as different members within the same close-knit family. The number of protons gives the element its name and its chemical personality, but the number of neutrons can vary even for atoms of the same element. These variations give rise to what we call isotopes. So, while all carbon atoms have 6 protons, some might have 6 neutrons, carbon -12, others 7 carbon -13, and some, like the famous carbon -14, 8 neutrons. They are all carbon, sharing the same fundamental identity, but with subtly different masses and sometimes different destinies. The nucleus, cradled in a cloud of electrons, is an arena of immense fundamental forces. It is incredibly tiny, yet contains almost all the atom's mass, a testament to the compact power of these two resident particles. The steady rhythm of protons defining identity and neutrons providing stability forms the bedrock of all matter around us, from the smallest speck of dust to the grandest galaxy. The quiet, powerful interplay of protons and neutrons within the atomic heart dictates how the universe is built and how it holds itself together in a delicate, enduring balance. The atomic nucleus, that impossibly dense and tiny heart of every atom, holds within its microscopic confines a bustling world of positive protons and neutral neutrons. You might imagine this tightly packed space, smaller than a whisper, smaller than the most delicate dream, as a kind of cosmic anomaly. For within it, a peculiar tension arises. The protons, each carrying a positive electric charge, naturally wish to repel one another. Like gentle magnets turned against their will, they push away, seeking distance, eager to scatter, left to their own devices. This fundamental electrical repulsion would tear apart every atom in the universe, scattering its very essence into a fine, undifferentiated dust. And yet here they are, nestled close, held in an astonishing silent embrace. This is where the universe reveals one of its most profound and subtle ballets, living the dance of forces. Overcoming the inherent push of electrical repulsion is a power of such immense strength that it defies our everyday understanding. It is the strong nuclear force, a guardian, a binder, the quiet architect of all matter as we know it. Imagine it not as a simple push or pull, but as an invisible, fervent hand, gently yet unyieldingly clasping together these tiny, vibrant particles. It is the most powerful of the 4 fundamental forces in the cosmos, a force so potent that it can overcome the very real, very insistent repulsion of protons, gluing them together into the stable nuclei that form the bedrock of our world. This force, however, is a study in magnificent paradox. While it reigns supreme in its strength, its reach is incredibly, almost impossibly, short. Think of it as a silent whisper that can only be heard in the most intimate proximity. Beyond a specific infinitesimal distance, its power vanishes almost entirely, like a dream dissolving at dawn. It doesn't stretch across the vastness of space, or even the expanse of an atom's electron cloud. No, its domain is solely within the nucleus itself, a microscopic realm where protons and neutrons must almost touch to feel its binding power. In this way, the strong nuclear force is like a fiercely protective spirit, fiercely loyal to its immediate family, but with little interest in the world beyond its tiny, bustling home. This delicate balance, this incredible strength, coupled with its ephemeral range, is what allows the universe to exist in its current, intricate form. Without the strong force, there would be no atomic nuclei, no elements heavier than hydrogen, No stars, no planets, and no living beings to ponder its mystery. It is the foundational glue, the silent agreement that allows matter to clump together, to form the rich tapestry of elements that builds everything from the dust in your living room to the farthest nebula. It is the reason the iron in your blood exists, the carbon in your bones, the oxygen you breathe. Each of these elements, forged in the hearts of stars long past, carries the imprint of this silent, powerful embrace at its very core. You might visualize the nucleus as a tiny, bustling town where the inhabitants, protons and neutrons, collectively known as nucleons, are constantly attempting to dance apart due to the electromagnetic repulsion. Yet, an invisible, immensely powerful web of connections holds them firmly in their places. This web is woven by the strong force, maintaining an order, a structural integrity that allows the nucleus to exist as a distinct, stable entity. It is a force that doesn't shout or command. Rather, it's simply findy, a sign be, a fundamental presence ensuring the quiet harmony of the atomic heart. Within this infinitesimally small space, its grip is absolute, creating a tiny bastion of stability against the universal tendency towards dispersal. And as you drift deeper into understanding this powerful, hidden force, you might feel a soft sense of reassurance, knowing that even at the smallest scales, there are profound, stable anchors holding reality together. The very existence of our complex universe, with its swirling galaxies and vibrant life, rests on this exquisite atomic architecture, silently maintained by the strong nuclear force. It is a force that doesn't just bind matter. In a way, it binds time and possibility, allowing for the slow, majestic unfolding of cosmic evolution. Its presence is a testament to the intricate and often paradoxical design of the universe. A universe where the most powerful forces often operate in the most confined, hidden spaces, shaping the very fabric of existence with a quiet, unwavering strength. Just as a family might have many members, each with their own unique quirks and personalities, so too do the elements have variations within their own kind. Imagine the carbon in your body, the oxygen in the air, or the iron in the earth. Each of these elements is defined by the number of protons resting peacefully within its atomic nucleus. This number is like a cosmic fingerprint, giving each element its unique identity and its place in the grand periodic table. But beneath this defining identity, there is a more subtle layer of variation, a nuanced difference among atomic siblings, the world of isotopes. Isotopes are like relatives from the same family, sharing the same surname, the element identity, but having a slightly different number of children, neutrons. So, while all carbon atoms, for instance, have exactly 6 protons, they might have 6, 7, or 8 neutrons. These subtle additions or subtractions of neutrons don't change the element's fundamental identity or its chemical personality. A carbon atom with 7 neutrons, carbon -13, will still behave chemically like a carbon atom with 6 neutrons. Carbon -12, they will still form the same types of bonds, engage in the same molecular dances, and participate in the same chemical reactions. Their electron clouds, which dictate their chemical behavior, remain essentially unchanged. Yet, these extra or fewer neutrons do impart subtle differences in their physical nature. They become slightly heavier or lighter, like 2 siblings with the same smile but different builds. This difference in mass is often negligible in our everyday experience, yet it holds profound implications for the silent stories that the universe tells. Some isotopes are perfectly content, existing in a stable, unchanging state for eons. They are the quiet, steady members of the atomic family, content to simply be. Carbon-12, the most common form of carbon, is one such example, sine a bedrock of stability. But then there are the more restless siblings, the radioactive isotopes. These atoms carry within their nucleus a slight imbalance, an excess of energy, or an awkward arrangement of protons and neutrons that leaves them feeling a little unstable. They are like a quietly vibrating string, always seeking a more harmonious tone. Over time, these restless nuclei will undergo a gentle transformation, slowly shedding their excess energy or rearranging their internal components until they reach a more stable configuration. This process, known as radioactive decay, is a spontaneous, quiet act of transformation, a journey from one atomic state to another. Carbon-14 is perhaps the most famous of these restless isotopes. It is a form of carbon that has 2 extra neutrons compared to its stable cousin, carbon-12, while present in only tiny amounts in our atmosphere. It is continually formed and incorporated into all living things. And then, once a plant or animal ceases to live, the delicate dance of carbon exchange with the atmosphere stops, and the carbon-14 within it begins its slow, steady decay. It becomes a silent, internal clock, ticking away the years, telling a quiet story about the passage of time. This ability of isotopes to mark the flow of ages is not just a scientific curiosity. It is a profound tool that allows us to gently pull back the veil of history, revealing the age of ancient artifacts, fossils, and geological formations. Beyond carbon, isotopes play a silent yet vital role across many fields. In medicine, specific radioactive isotopes can be carefully introduced into the body, acting as invisible trackers to help diagnose diseases or target treatments, illuminating the intricate pathways of our biology from within. In geology, the decay of long-lived isotopes allows scientists to date rocks and understand the deep history of our planet, tracing its formation and evolution over billions of years. Each isotope, whether stable or gently transforming, contributes its unique voice to the grand chorus of matter, whispering its specific properties and offering its quiet insights into the very nature of existence. They are the subtle variations within sameness, demonstrating that even at the fundamental level of the atom, individuality and a spectrum of being exist. The quiet differences in their nuclear composition lead to distinct fates, some content to simply endure, others destined to slowly transform, all contributing to the rich, dynamic tapestry of the cosmos. As you consider these subtle shifts in atomic identity, you might sense a deeper layer of complexity in the universe, where even the most fundamental building blocks have their own quiet stories and destinies. Not all atomic nuclei are content to simply exist in their initial state. Some, as we have gently touched upon, are inherently unstable. They are like quiet, vibrating instruments, holding within them an excess of energy, a subtle disquiet that eventually leads them to seek a more peaceful, balanced configuration. This natural journey towards stability, the spontaneous release of energy and particles, is known as radioactivity, a fundamental process through which the universe itself slowly transforms. It is not an explosion or a violent outburst, but rather a slow, deliberate breathing, a quiet metamorphosis of the atomic heart. Imagine a nucleus that has grown too large, or perhaps has an imbalanced ratio of protons and neutrons, making it feel a little unwieldy. To find greater comfort, it might choose to shed a small, compact cluster of particles. This is alpha decay. In this process, the nucleus gently expels what is essentially a helium nucleus, 2 protons and 2 neutrons, bound tightly together. It is like a large, heavy atom sighing, letting go of a small, stable piece of itself to become a slightly lighter, often more balanced atom of a different element. This shedding changes not only the atom's mass, but also its identity, as the number of protons, its defining feature, has now decreased. Then there is beta decay, a more subtle and internal transformation. Here the nucleus doesn't expel a whole chunk of itself, but rather undergoes an internal rearrangement. Most commonly, a neutron within the nucleus quietly transforms into a proton, simultaneously emitting an electron, and another tiny ghostly particle called an antineutrino, which drifts away almost unnoticed. This transformation changes the element's identity, as the proton count increases by 1, while the mass number remains largely the same. In another form of beta decay, a proton can transform into a neutron, emitting a positron, the electron's antimatter twin. These internal shifts are like a soft retuning of the nucleus, adjusting its composition to find a more harmonious state. And finally, there is gamma decay, perhaps the most ethereal of all. This form of decay doesn't involve a change in the nucleus's identity or its number of protons and neutrons. Instead, it is purely a release of excess energy, often occurring after an alpha or beta decay has left the nucleus in an excited state. The nucleus simply settles down like a child, letting out a long, quiet sigh after a period of excitement. It releases this energy in the form of high-energy photons, 4 packets of light known as gamma rays. These rays, unseen and unfelt by us directly, carry away the excess energy, allowing the nucleus to return to a calm ground state. It is a fundamental way in which the nucleus releases its inner warmth without altering its essential being. These processes of radioactive decay are not mere curiosities. They are the silent engines of transformation throughout the natural world. They are responsible for the slow internal heat that keeps Earth's core warm, driving geological processes like plate tectonics and volcanism. They are the basis of nuclear power, harnessing the energy released from these atomic metamorphoses to generate electricity in a controlled, powerful cascade. And in medicine, these same quiet transformations are carefully utilized to image our bodies, diagnose illnesses, and target diseased cells, acting as invisible tools that help us understand and heal. The half-life, a unique characteristic of each radioactive isotope, is the time it takes for half of a given sample of unstable nuclei to undergo decay. It is not a sudden event, but a steady probabilistic unraveling, like a quiet hourglass where each grain of sand is an atom transforming. This half-life can range from fractions of a second to billions of years, making these decaying nuclei nature's most precise and patient clocks. As you consider the silent, continuous dance of decay within the heart of matter, you might feel a profound sense of the universe's dynamic nature. Nothing truly stands still, even at the deepest atomic level. Elements are born, they live, they transform, they release their energy, and in doing so, they weave the ongoing story of cosmic evolution. This quiet shedding, this breathing out of energy and particles, reminds us that even the most fundamental building blocks of reality are engaged in a constant, beautiful flux, a never-ending journey toward balance and renewal. And as these quiet transformations unfold, you can rest in the knowledge that this ceaseless motion is part of the deep, underlying rhythm of the universe. Because tonight, we continue our quiet journey, not through the grand swirling expanse of our galaxy, but inward, much deeper, to the very fabric of existence. We'll explore the unseen connections, the subtle shapes, and the gentle dances that build everything you touch, everything you feel, everything you are. Let your mind drift, your breath soften, and allow these quiet truths to guide you into a profound and restful sleep. Atoms, you see, are rarely content to be alone. Like tiny invisible beings, they seek connection, drawn to each other by unseen desires, by fundamental forces. They don't just exist, they interact, they partner, they form silent, intricate bonds that are, in their own quiet way, the most fundamental form of companionship in the universe. Imagine these bonds not as rigid chains, but as invisible hands reaching out, gently grasping or softly intertwining. It is through these subtle embraces that the vast symphony of matter begins to play, building everything from a single droplet of water to the towering mountains that rest beneath a star-strewn sky. One of the most intimate of these connections is called a covalent bond. Picture two atoms, side by side, finding a quiet understanding, a shared purpose. Instead of one giving to the other, they decide to share. They offer up their outermost electrons, letting them orbit not just one nucleus, but both. It's like two solitary dancers, discovering they can move more gracefully, more stably, by holding hands and turning together. This shared existence, this quiet pact, makes them stronger, more content. Think of a water molecule, H2O. The oxygen atom, with its gentle pull, shares electrons with two hydrogen atoms. They are not merely touching, they are interlinked. Their destinies intertwined by these shared electrons, moving in a silent, delicate dance between them. This sharing is not fleeting. It forms a deep, stable connection, like a whispered promise in the dark, creating molecules that are incredibly resilient, forming the very essence of the air you breathe, the molecules that carry the scent of a distant flower or the sugars that sweeten your tea. Each shared pair of electrons is a silent vow, holding atoms together in an enduring embrace, forming the bedrock of organic chemistry, the very basis of life itself. These shared electron clouds are like soft, overlapping blankets, providing comfort and stability to the atoms involved, allowing them to exist in a state of lower energy, a more peaceful configuration. It is a gentle compromise, a subtle give and take, where both participants find contentment in the union. And from these simple shared acts, an entire world of complex substances emerges, all quietly held together by these invisible, enduring hands. Then there is another kind of embrace, a different rhythm of connection, known as an ionic bond. Here, the interaction is less about sharing and more about a generous transfer, a quiet exchange. Imagine one atom, perhaps a little more robust, with a stronger magnetic pull, gently convincing another atom to let go of an electron. It's not a forceful taking, but a quiet offering, a subtle persuasion. One atom, in releasing an electron, becomes slightly positive, like a tiny star with a missing ray of light. The other, in accepting that electron, becomes slightly negative, like a quiet moon gathering more of the sun's glow. And like two oppositely charged magnets, They are then drawn to each other with a soft, persistent pull, forming a stable, balanced pair. Think of common table salt sodium chloride, NaCl. The sodium atom in its electron shell has a single electron. It would rather release to achieve a more stable, serene state. Chlorine, on the other hand, quietly yearns for just one more electron to complete its own peaceful configuration. So, sodium gently offers its electron to chlorine. Sodium becomes positively charged. Chlorine becomes negatively charged. And in that moment, a quiet magnetic attraction forms between them, pulling them together into a stable, crystalline lattice. This connection is strong, yet often invisible in its individual components, only revealing its power when countless such bonds gather to form a tangible substance, like the shimmering crystals of salt. It's a silent, cosmic magnetism at play, a fundamental attraction that organizes vast quantities of atoms into ordered structures, like unseen dancers forming precise patterns in a grand, unseen ballroom. It's a delicate balance of giving and taking, a fundamental rhythm that sculpts the very landscapes of our world, from the minerals in the earth to the salts in the vast, deep oceans. These are the quiet social interactions of atoms, the gentle ways they connect, creating the endless array of materials that surround us, each one a testament to these unseen, fundamental bonds holding the universe softly in its intricate design. Molecules, you see, are not simply random clusters of atoms. They are exquisitely designed miniature sculptures, each with a precise invisible architecture. Just as a potter molds clay into a specific form, or an architect drafts the blueprint for a building, atoms, once bonded, arrange themselves into distinct, predictable shapes. These aren't haphazard piles. They are graceful, geometric formations, determined by the delicate balance of electron repulsion and the angles of their shared connections. It's as if each molecule has its own unique, silent blueprint, a hidden geometry that dictates its every interaction, its every property. And these forms, though microscopic, have a profound impact on the macroscopic world you experience every waking moment. Consider, for a moment, the humble water molecule, H2. It's not a straight line, nor is it a perfect triangle. Instead, it has a gentle, inviting V-shape, a subtle bend like two arms held slightly open. This isn't arbitrary. The central oxygen atom holds two hydrogen atoms, and also has two lone pairs of electrons. Sunday electrons not involved in bonding, but still exerting a quiet, subtle repulsion. These electron pairs, like shy friends, push the hydrogen atom slightly downward, creating that characteristic bent shape, an angle of about 104.5 degrees. This seemingly insignificant curve is profoundly important. It means one side of the water molecule is slightly negative, and the other side is slightly positive. This polarity, this gentle tilt in its electrical balance, is why water is such an extraordinary solvent, why it can dissolve so many substances, why it's the universal medium for life. It's a silent, hidden design, a microscopic architectural choice that makes oceans possible, that keeps your body hydrated, that allows life to flourish. This bent geometry is a quiet secret, whispering to countless other molecules, inviting them to dissolve, to interact, to join in the dance of life. Then, there are molecules that embrace a more symmetrical, three-dimensional form, like the tetrahedral shape. Imagine a perfect four-sided pyramid, with one atom at the very center and four other atoms reaching out to its corners. Methane shock is a perfect example. A central carbon atom forms a quiet, stable bond with 4 hydrogen atoms, each equally spaced in a beautiful symmetrical arrangement. This tetrahedral shape is a fundamental building block, a testament to carbon's ability to form strong, versatile connections. It is a structure of immense stability, like a perfectly balanced sculpture, allowing carbon to form the backbone of nearly all organic molecules, from the simplest sugars to the most complex proteins and DNA. Even the immense hardness of a diamond, a pure carbon structure, arises from an endless network of these interconnected tetrahedrons, each carbon atom silently holding onto 4 others, forming an unbreakable crystalline embrace. This geometry provides strength and resilience, a silent scaffolding that supports so much of the physical world. It is a shape that speaks of quiet strength, of balanced forces, of a fundamental order. And some molecules choose a simpler, more direct path, arranging themselves in a straight line, a linear form. Carbon dioxide, Colorado soup, is a familiar example. The central carbon atom sits serenely between 2 oxygen atoms, forming a perfectly straight line, a quiet, symmetrical arrangement. This linearity, this simple, unbending structure contributes to its properties as a gas, its ability to move freely and not cling to other molecules as water does. Each molecular shape, whether bent, tetrahedral, or linear, is not a coincidence. It is a precise outcome of the silent conversations between electrons, a fundamental expression of the forces that bind atoms together. These invisible geometries dictate everything from a molecule's melting point to its taste, its smell, its biological activity. They are the unseen blueprints of the universe, shaping the very essence of matter, determining how it interacts, how it exists, how it contributes to the vast, quiet symphony of creation. Understanding these shapes is like listening to the whispered language of the universe, revealing the elegant order hidden within the smallest scales of existence, guiding all matter in its beautiful silent dance. Imagine, if you will, that all the atoms in the universe are engaged in a cosmic dance. The way they move, the way they hold each other, the space they keep between them, defines the very nature of the matter you perceive. The 3 fundamental states of matter, solid, liquid, and gas-dyed, are simply different choreographies, different rhythms in this grand, silent ballet of particles. Each state whispers its own story of connection, freedom, and the gentle energy that animates it. In the solid state, atoms perform a tightly choreographed, elegant collective dance. They are held close, almost intimately, by strong, persistent bonds, forming a fixed, orderly arrangement, like a vast, invisible grid. Yet, they are not entirely still. Each atom, despite being locked into its position, vibrates gently, a quiet tremor, like a tiny bell softly ringing in place. Imagine them as dancers standing in a perfect formation, each swaying gently to an unheard rhythm, never breaking their hold on their neighbors. This is the essence of solidity, strong attractions, minimal movement, and a defined shape. Think of a crystal shimmering in the light, or the unyielding strength of a diamond. Its atoms are in a constant, quiet tremor, a subtle hum of internal energy, yet they maintain their fixed positions with steadfast grace. They are in a perpetual state of subtle oscillation, a silent song sung in place, reflecting the deep stability and quiet order that defines everything from the bedrock beneath your feet to the delicate structure of a snowflake. This is matter in its most settled, most composed form, a gentle hum of stillness. As energy is gently added, perhaps as a soft warmth, the dance changes. The atoms gain a little more vigor, a little more freedom, and transition into the liquid state. Here, the bonds between them loosen, like hands that are still connected but no longer held so tightly. Atoms can now slide past each other, flowing and gliding in a continuous, graceful waltz. There is still a sense of connection, a subtle intimacy, but with far greater fluidity. Liquids take the shape of their container, adapting to their environment with a quiet elegance, like a slow, meandering river finding its own path. They whisper of adaptability, of gentle currents, of a constant, subtle rearrangement. Think of a peaceful stream, or the way a droplet of mercury shimmers and rolls. The atoms are always in motion, maintaining contact, but never for too long with any single partner, always subtly changing their neighbors as they drift and flow. It is a state of beautiful compromise, of connection without rigidity, of movement without complete separation. This is matter in its more yielding, more adaptable form, constantly shifting, subtly reshaping, always finding its level with a quiet, persistent grace. The liquid state is a continuous, soft murmur of movement, a gentle current of particles, and with even more energy, perhaps a rising warmth, the dance transforms once more into the boundless, energetic ballet of the gaseous state. Now, the bonds between atoms are almost entirely broken, like dancers who have finally let go of each other and are free to roam the entire ballroom. And atoms move rapidly, independently, in straight lines, only occasionally glancing off each other in fleeting, soft collisions. They fill whatever space is available to them, expanding outward with an unseen quiet energy. Imagine them as solitary stars, drifting across vast cosmic distances, occasionally encountering another, but mostly reveling in their immense freedom. Gases have no fixed shape or volume. They are elusive, ethereal, often invisible. Think of the air you breathe, a vast ocean of gas molecules, moving at incredible speeds, yet in a tranquil, silent dance all around you. This is matter in its most liberated, most dispersed form, a constant, silent explosion of movement. Each atom is a tiny world unto itself, charting its own course, yet collectively, they exert a gentle, pervasive pressure. It is a state of incredible emptiness, punctuated by fleeting encounters, a constant, silent whisper of motion across vast, unseen spaces. This is the most energetic, yet often the most serene, of the atomic dances, filling the quiet voids with invisible life. These transitions, from solid to liquid to gas, are not violent changes, but gentle shifts in the rhythm of the atomic dance, brought about by the subtle influence of temperature soaring. The quiet energy that breathes life into matter, the molecule of water, H2O, seems so simple at first glance. 2 hydrogen atoms, 1 oxygen, a humble trio. And yet, within this modest arrangement lies a universe of unique properties that make life as we know it possible. Imagine, if you will, the oxygen atom at the center, a slightly larger, more embracing presence, holding the 2 smaller hydrogen atoms close, almost like a gentle, wide V-shaped embrace. This isn't a straight line, but a subtle bend, and this geometry is the first secret quietly shaping everything that follows. Because of the way oxygen holds onto electrons, with a slightly stronger grip than hydrogen. This tiny molecule isn't perfectly balanced. It has a slight positive charge on the hydrogen side and a slight negative charge on the oxygen side. It is what we call a polar molecule, like a tiny gentle magnet with a subtle pull in different directions. And it is this polarity that allows water to form what we call hydrogen bonds. Picture these bonds not as rigid connections, but as a soft, almost ethereal embrace between neighboring water molecules. The positive hydrogen of one molecule is gently drawn to the negative oxygen of another, creating a web, a delicate, ever-shifting network of connections. It is a silent, constant dance, a whisper of attraction that binds these molecules together, giving water its extraordinary coherence. This network of hydrogen bonds is why water has such a relatively high boiling point, why it doesn't simply evaporate away from our planet in the gentle warmth of the sun. These molecules need more energy, more urging, to break free from these subtle, loving holds. They cling to each other, creating a liquid that feels substantial, that flows in rivers and fills our oceans, a liquid that can hold and carry warmth through vast distances, gently moderating the climate of our world. And then there's the incredible phenomenon of ice. Most substances, as they cool and solidify, become denser, drawing their constituent parts closer. But water, through the unique geometry of its hydrogen bonds, performs a quiet magic. As it crystallizes into ice, these bonds arrange themselves into a more open, spacious lattice, a delicate, airy structure. This means ice is less dense than liquid water, allowing it to float. Imagine the vast oceans, the deep lakes gently covered by a blanket of ice in winter. This floating ice acts as a protective shield, insulating the water beneath from the biting cold above, allowing life to continue its quiet rhythm in the depths. Without this gentle floating guardian, our waters would freeze solid from the bottom up, extinguishing most aquatic life and drastically altering the very face of our planet. It is a subtle, yet profound, act of cosmic kindness woven into the very fabric of H2O. Furthermore, these hydrogen bonds give water its remarkable ability to dissolve an incredible array of substances, earning it the title of the universal solvent. Because of its gentle polarity, water molecules can surround and softly pull apart other polar or charged molecules, holding them in a dissolved state. It is as if water is an ever-open, welcoming host, inviting a myriad of chemical guests to join its liquid dance. This solvent power is absolutely essential for life, allowing nutrients to be transported, waste products to be carried away, and countless chemical reactions to unfold within the fluid environment of every living cell. From the tiny, shimmering dewdrop on a leaf, to the vast, swirling currents of the ocean, to the very fluid that courses through your veins, water is everywhere, performing its quiet miracles. Its unique atomic structure, the subtle bend, the gentle polarity, the embracing hydrogen bonds, all conspire to create a substance that is both simple and profoundly complex. A silent orchestrator of life, a constant comforting presence in the grand tapestry of the universe. It flows and ebbs, a fluid cradle, shaping landscapes and nurturing the delicate spark of existence. A truly extraordinary journey from 3 atoms to the world. Now, let us turn our attention to the silent, powerful heart of matter itself, to processes that shape worlds and hint at energies almost beyond our comprehension. Imagine Deep within the nucleus of an atom, a delicate balance of forces holding its tiny components together in a stable embrace. But for some larger, heavier atoms, this balance can be precarious, like a perfectly still top that, with the slightest tremor, begins to wobble. This is where nuclear fission enters the story. Fission is the process by which a heavy atomic nucleus, often unstable, gently splits into two or more lighter nuclei, releasing an astonishing amount of energy in the process. It is not an explosion in the common sense, but a quiet, almost reluctant transformation, a seeking of a more stable state. Think of it as a heavy, overfilled vessel, finding relief by gently dividing its contents. The discovery of fission in the late 1930s unveiled a new frontier of energy and understanding. Scientists found that when a neutron, a neutral particle, gently nudges the nucleus of certain heavy atoms, like uranium or plutonium, that nucleus can become so unsettled that it elongates and then divides. And here is the profound part. When it splits, it doesn't just form new, lighter nuclei, but it also releases a few more neutrons. These newly released neutrons, moving at high speeds, can then go on to nudge other heavy nuclei, causing them to split in turn. This creates a cascading sequence, a chain reaction, like a line of dominoes falling, each one triggering the next. But instead of a quiet click, each falling domino in this atomic chain releases immense bursts of energy, all from the transformation of a minuscule amount of mass into pure energy, as predicted by Einstein's famous equation. EPRED. In controlled environments, such as nuclear power plants, this chain reaction is carefully managed and slowed, like taming a powerful wild river into a gentle flowing stream. The energy released heats water, turning it into steam, which then drives turbines to generate electricity. It is a silent hum, a deep, steady warmth that powers our cities and lights our homes, providing vast amounts of clean energy without burning fossil fuels. It represents humanity's ingenuity in harnessing one of nature's most fundamental forces for the benefit of civilization. Yet, like many profound discoveries, fission holds a dual nature, a quiet power that can both cradle and shatter. The uncontrolled chain reaction is the principle behind atomic weapons, a stark reminder of the immense destructive potential inherent in the very fabric of matter when unleashed without restraint. The mushroom cloud, a terrifying symbol of immense energy concentrated in a single, devastating moment, serves as a permanent shadow, a deep ethical challenge to humanity's scientific prowess. So, as you drift through this story of splitting atoms, remember the delicate balance. A force so powerful that it can provide quiet, clean light for millions, or, in its unconstrained form, bring about unimaginable devastation. It is a testament to the fact that within the smallest particles of our world lies an energy vast enough to reshape our future, demanding both our reverence and our utmost responsibility. It is a reminder of the quiet power that rests within the very heart of existence, waiting to be understood, to be harnessed, to be respected. From the splitting of atoms, let us now turn to their gentle embrace, to a process that powers the stars above, a dream of limitless energy here on Earth. Imagine, if you will, the opposite of fission, not the breaking apart of heavy nuclei, but the gentle merging of light ones. Two small particles coming together to form something larger, something new, releasing an even more astonishing amount of energy in the process. This is the magic of nuclear fusion, the very furnace that ignites the sun and every shimmering star in the night sky. Deep within the heart of our sun, under unimaginable pressure, and at temperatures reaching millions of degrees, hydrogen nuclei, the simplest of all atoms, are gently pushed together. These are not collisions in a destructive sense, but a profound, forceful dance, where the positive charges of the nuclei normally repel each other fiercely. Yet, under such extreme conditions, they overcome this natural aversion, drawing close enough for the mighty strong nuclear force to take hold, binding them into heavier helium nuclei. When these light nuclei fuse, a small amount of their mass is once again transformed into pure, radiant energy. This is the source of all starlight, the gentle warmth that bathes our planet, the ultimate energy engine of the cosmos. It is a continuous, quiet, yet immensely powerful process, where billions upon billions of these fusion events occur every second, releasing the energy that sustains entire solar systems. Imagine the quiet glow of a distant star. That is the gentle breath of fusion, ceaselessly creating light and heat across the vast canvas of space. For decades, scientists have dreamt of bringing this stellar power down to Earth, of building artificial suns in our laboratories. The promise is profound, virtually limitless, clean energy. The fuel, primarily isotopes of hydrogen, is abundant in seawater, and the byproducts of fusion are mostly non-radioactive helium, a gentle echo of creation, far less problematic than the waste from fission. It is a beacon of hope, a potential solution to our planet's energy needs that could transform our civilization, offering warmth and light without the shadows of environmental impact. However, replicating the conditions of a star on Earth is an immense challenge. It requires creating and containing plasmas, superheated gases where atoms have been stripped of their electrons, at temperatures far hotter than the sun's core. These swirling, energetic plasmas must be held in place, often by powerful magnetic fields, preventing them from touching any material walls and instantly vaporizing them. It is a delicate balancing act, a subtle art of containment, pushing the boundaries of engineering and physics. Scientists across the globe are working patiently, meticulously to unlock this secret. Giant fusion reactors, known as tokamaks or stellarators, are being built, designed to gently squeeze and heat hydrogen isotopes until they begin to fuse, creating miniature, controlled starlight for fleeting moments. Each small success, each tiny burst of energy, is a whisper of the future, a testament to humanity's quiet perseverance in seeking to understand and harness the deep, cosmic forces that govern our universe. You can almost imagine the gentle humming of these future devices, a deep, steady thrum echoing the silent, radiant heart of a star. It is a dream of abundance, a vision of a world powered by the very essence of creation, a soft glow promising a cleaner, brighter future. This journey into fusion is a long one, a patient pursuit, but it is driven by the profound realization that within the gentle embrace of the lightest atoms lies the ultimate key to sustainable power, a quiet, luminous dance of energy waiting to be fully understood and brought home. Your body, a universe of intricate processes and quiet wonders, holds secrets far beyond what the eye can see. And within this deeply personal universe, the tiny silent language of atoms offers a profound pathway to understanding, and sometimes to healing. Imagine the most delicate touch, an invisible guardian working within you, revealing truths hidden beneath the surface of skin and bone. This is the quiet magic of atoms in medicine. Consider for a moment the soft hum of an MRI machine. Its name, magnetic resonance imaging, whispers of the very core of this atomic dance. At its heart lies the humble hydrogen atom, abundant in the water that flows through every cell of your being. Each hydrogen atom carries a single proton, and this proton possesses a tiny innate spin like a miniature top turning ceaselessly. When placed within a powerful magnetic field, these countless tiny atomic spins align, like compass needles pointing north, settling into a gentle, ordered stillness. Then, a brief radio frequency pulse washes over the body, a fleeting wave of energy. This gentle nudge briefly tips some of these aligned protons out of their equilibrium, causing them to absorb the energy and flip their tiny spins. But this state is transient, a momentary diversion. As the radio pulse fades, these protons softly relax, returning to their aligned state within the strong magnetic field. And in that moment of relaxation, they release the absorbed energy, sending out faint, unique radio signals of their own. These subtle whispers of energy are then carefully detected by the MRI scanner. The speed at which these protons relax, the particular echo they send back, varies ever so slightly depending on the type of tissue they reside in, whether it is bone, muscle, fat, or the soft, watery tissue of the brain. The MRI computer, a patient listener, collects these myriad signals, mapping them with astonishing precision. It paints a picture, not of light, but of the magnetic properties of these tiny atomic spins, creating incredibly detailed images of your internal landscape, from the intricate folds of your brain to the delicate structures of your joints. It is a journey into the body's quiet currents, a way to see what lies unseen, all guided by the gentle, rhythmic dance of atoms. Beyond these magnetic echoes, atoms also offer a luminous pathway for diagnosis and treatment through their inherent instability. Some atoms, called radioactive isotopes, hold within their core an excess of energy, a gentle restlessness. They seek a more stable form, and in doing so they undergo a quiet transformation, releasing this surplus energy in the form of particles or gamma rays. This process, known as radioactive decay, is a predictable natural rhythm, a slow exhalation of energy. One remarkable application of this decay is in PET scans, positron emission tomography. Here, a special type of radioactive isotope, often attached to a glucose molecule, is introduced into your body. Glucose, as you know, is the body's primary fuel, eagerly consumed by cells. By tagging glucose with a radioactive tracer, scientists can follow its path like a tiny luminous guide. As cells metabolize this radioactive glucose, the isotope undergoes a particular type of decay, releasing tiny particles called positrons. When a positron meets an electron, its antimatter counterpart, they gently annihilate each other, converting their mass into pure energy, which is then emitted as two gamma rays traveling in opposite directions. These paired gamma rays are detected by the PET scanner, which then reconstructs a luminous map of your body's metabolic activity. Areas of high glucose uptake, such as rapidly growing tumors or regions of intense brain activity, light up with a soft, revealing glow. It's like watching the quiet energy consumption within your own cells, seeing which parts are most active, which are consuming the most fuel. This invisible light allows doctors to peer into the functional workings of organs and tissues, not just their structure, offering a deeper understanding of health and disease. And when it comes to healing, particularly in the battle against cancer, The very energy released by these unstable atoms can be harnessed with profound intention. Radiation therapy carefully directs high energy particles or waves, often gamma rays or X-rays, at cancerous cells. These energetic streams are like precise, focused whispers designed to damage the DNA within the rapidly dividing tumor cells, preventing them from growing and spreading. Healthy surrounding tissues, more resilient and capable of repair, are carefully spared as much as possible. This delicate balance, this powerful yet precise application of atomic energy, transforms a destructive force into a profound instrument of healing. It is a testament to the deep understanding we have gained of the atomic world Tunda, that something so tiny, so often unseen, can be coaxed into revealing our body's inner secrets, or guided to mend what is broken. The atoms, in their silent and ceaseless work, become our gentle guides, our invisible guardians, watching over our health with a quiet, luminous care. Every ancient artifact, every fossilized bone, every delicate strand of organic matter whispers a story of the past. But how do we, across the vast gulf of time, decipher these silent narratives? How do we listen to the echoes of ages long gone? The answer lies within the very atoms that compose these remnants, specifically, a special kind of carbon. It's a method known as carbon-14 dating, and it's like a quiet internal clock patiently ticking within all living things. To understand this atomic timepiece, we must first journey high above the Earth, into the embrace of its atmosphere. Here, cosmic rays, energetic particles streaming from outer space, gently collide with nitrogen atoms. These celestial impacts transform some of the stable nitrogen atoms into a new, slightly heavier version of carbon, carbon-14. Unlike its more common sibling, carbon-12, carbon-14 is radioactive, meaning its nucleus is unstable, carrying that gentle restlessness we spoke of earlier. This newly formed carbon-14 then mingles with the regular carbon-12, slowly drifting down to Earth and entering the vast carbon cycle. Plants absorb carbon dioxide from the atmosphere during photosynthesis, incorporating both carbon-12 and carbon-14 into their tissues. Animals in turn consume these plants or other animals, thereby incorporating the same ratio of both carbon isotopes into their own bodies. As long as an organism is alive, breathing, eating, growing, it continuously exchanges carbon with its environment. This means that throughout its life, the ratio of carbon-14 to carbon-14 to carbon-12 in its tissues remains relatively constant, mirroring the atmospheric ratio. It's like a steady, gentle intake, a constant refresh. But then, a profound change occurs. When an organism dies, it ceases to exchange carbon with its environment. The flow stops. The intake ends. At this precise moment, the silent atomic clock begins its patient count. The stable carbon-12 atoms remain unchanged, enduring witnesses to time's passage. However, the unstable carbon-14 atoms, with their gentle restlessness, begin their slow, predictable decay. They transform back into nitrogen atoms, releasing energy in the process. This decay happens at a remarkably steady and known rate. After approximately 5,730 years, exactly half of the original carbon-14 atoms in the dead organism will have decayed. This period is known as its half-life. After another 5,730 years, half of the surviving carbon-14 will have decayed, and so on. It's a quiet, exponential dwindling, a gradual fading of a luminous presence. By measuring the remaining ratio of carbon-14 to carbon-12 in an ancient organic sample, be it a fragment of bone, a piece of charcoal from an ancient fire, a wooden artifact, or even a preserved textile, scientists can precisely calculate how many half-lives have passed since the organism died. The less carbon-14 there is relative to carbon-12, the older the sample. It's like listening to a faint, distant echo, deciphering the duration of its journey through time. This powerful method has allowed us to unlock countless secrets of our past. It has dated ancient human settlements, revealing the timelines of early civilizations. It has traced the migrations of prehistoric peoples, mapping their quiet journeys across continents. It has authenticated invaluable artifacts, separating genuine relics from later imitations. From the delicate textiles woven by an ancient hand to the grand wooden structures of forgotten temples, carbon-14 dating offers a window into lives lived long ago. A gentle hand reaching across the millennia. It's a scientific marvel that connects the invisible dance of subatomic particles to the grand sweep of human history and the quiet rhythms of the natural world. Each decaying atom of carbon-14 is not just fading away. It is leaving a subtle mark, a whisper in the fabric of time, allowing us to piece together the tapestry of existence, one quiet, measured moment at a time. It reminds us that even in death, the atoms continue their profound work, revealing the enduring stories of life. Look closely at your hand. Feel the quiet warmth of your skin, the strength of your bones, the gentle pulse of your blood. Every single atom that comprises this intricate, living vessel of yours, every carbon, every oxygen, every iron atom has a story, a cosmic lineage that stretches back across billions of years to the very heart of the universe itself. You are, in the most profound sense, made of stardust. Imagine the earliest moments of our universe, a time of immense heat and boundless energy. In that primal crucible, only the lightest elements could form, hydrogen and helium, the original cosmic gases. All the heavier elements, the ones that build planets, form mountains, and sculpt the very essence of life, had to wait for a more patient, more profound architect, the stars. Stars are the universe's ancient alchemists, magnificent furnaces where the fundamental transformation of matter takes place. Picture a colossal cloud of hydrogen and helium, slowly collapsing under its own gentle gravity. As the pressure and temperature at its core intensify, hydrogen atoms begin to fuse, pressing together in a fiery dance to form helium. This process, nuclear fusion, releases an astonishing amount of energy, the very energy that makes stars shine with such brilliant, enduring light. This is the birthplace of the sun, and indeed, every star you see twinkling in the night sky. But the story doesn't end with helium. As a star continues its long, luminous life, its core steadily builds up heavier and heavier elements through successive fusion reactions. Helium atoms fuse to form carbon. Carbon fuses to form oxygen. Further reactions in the hearts of truly massive stars slowly build up elements like silicon, sulfur, and eventually iron. Each new element is forged in the star's fiery embrace, a quiet whisper of creation within its luminous heart. Iron, however, marks a turning point. Fusing iron requires more energy than it releases. meaning the star can no longer sustain itself through this process. For the most massive stars, this leads to a dramatic and spectacular finale, a supernova. Imagine an ancient star, having lived for millions of years, suddenly collapsing inward under its own immense gravity, then exploding outward in a burst of unimaginable power, briefly outshining entire galaxies. This isn't just a cosmic spectacle, it is a cosmic dispersal. In that cataclysmic explosion, temperatures and pressures soar to such extremes that even heavier elements beyond iron, are rapidly formed and then scattered across the vastness of space. Gold, silver, uranium, these precious elements and countless others are born in the violent, beautiful death throes of a supernova. These stellar remnants, the newly forged elements, are then flung out into the cosmic void, mingling with the vast clouds of gas and dust that drift between stars. Over immense spans of time, these enriched clouds, now containing a richer tapestry of elements, begin to coalesce once more under gravity's gentle pull. New stars are born from this refreshed cosmic material, and crucially, new planetary systems begin to form around them. The atoms that once danced in the fiery heart of a long-dead star, or were scattered in its final luminous breath, now find new homes. They gather, they combine, they build. They form the rocky core of a young planet. They condense into the oceans. They form the very atmosphere. And ultimately, billions of years after their fiery birth, these very atoms, these ancient travelers, find their way into the delicate, intricate structures of living beings. The carbon in your DNA, the oxygen you breathe, the iron in your blood, each carries the indelible mark of a stellar nursery, a cosmic forge. You are literally composed of the remnants of ancient stars, a living, breathing testament to the universe's endless cycle of creation and destruction, of death and rebirth. This understanding is not just a scientific fact, it is a profound connection. It means that the elements within you have journeyed across unfathomable distances, through cosmic epochs, to become this unique, conscious entity that is you. You are a whisper of ancient light, a collection of stardust animated by the universe's own endless curiosity. And as you rest, remember this quiet truth: you carry the universe within you, a shimmering tapestry of cosmic history, softly glowing in the dark. There are whispers in the universe, faint echoes of what might have been or what could still be. We speak of particles, the tiny building blocks that compose all that we see, all that we are. But for every particle, there exists a ghost, a mirror image crafted from the same cosmic loom, yet utterly opposite in its very essence. This is the realm of antimatter. Imagine a world where everything you know has an inverse. A world where an electron with its gentle negative charge is met by its twin, the positron, identical in mass, yet carrying a positive charge. A proton, the sturdy core of an atom, finds its doppelganger in the antiproton, equally massive but oppositely charged. These are not merely reflections, but fundamental counterparts, born into existence as a delicate cosmic balance. When a particle and its antiparticle meet, it is not a clash, but a quiet, instantaneous vanishing. They do not collide and bounce away. Instead, they embrace, dissolving entirely into pure energy. A soft burst of light, a gentle exhalation of the universe itself. It's as if two opposing threads of creation when woven together, unravel completely, leaving behind only the radiant memory of their brief existence. This process, known as annihilation, is one of the most profound displays of cosmic symmetry, turning matter directly into light, just as light can. Under the right circumstances, birth matter and antimatter in equal measure. In the earliest moments of our universe, in the fiery infancy of the Big Bang, matter and antimatter were born in almost perfect symmetry. For every speck of dust that would one day become a star, a planet, or even you, there was an equal and opposite speck. And yet, something shifted. A tiny, almost imperceptible imbalance. Perhaps one part in a billion tipped the scales. For some reason, as the universe cooled and expanded, slightly more matter survived than antimatter. The rest, the vast majority of matter and antimatter, met their inevitable gentle end, transforming into a sea of photons that still fill the cosmic tapestry today. And it is from that minute surplus, that whisper of remaining matter, that everything around us, every galaxy, every breath, every thought, eventually coalesced. It is a quiet miracle, a cosmic lottery where matter was the unlikely victor, allowing for the slow, unfolding story of stars and life to begin. You are, in a very real sense, made of the universe's fortunate leftovers, drifting quietly through a cosmic sea where your exact opposite could exist. A phantom twin shimmering in a distant, unseen corner of reality. We float through the night, carried by a river of starlight, and yet, our perception of this vast expanse is still largely incomplete. Imagine gazing at a magnificent forest, but only being able to see the leaves and branches, while the ancient unseen roots that anchor it to the earth remain hidden. This is somewhat akin to our current understanding of the cosmos, where the familiar matter that forms stars, planets, and ourselves accounts for a mere fraction of its total being. The vast majority, the silent, invisible scaffold, and the accelerating push, remain largely unknown. This unseen foundation is known as dark matter. It does not reflect, absorb, or emit light, making it utterly invisible to our most powerful telescopes. It is a quiet, ethereal presence, detectable only through the gentle, persistent tug of its gravity. We see its influence in the way galaxies spin like grand cosmic pinwheels. They rotate far too quickly for the visible stars alone to hold them together. Something else, a massive, unseen halo, must be cradling them, guiding their slow dance through space. Without this invisible embrace, galaxies would simply unravel, their stars flung out into the lonely dark. It acts like an invisible glue, a silent architect, weaving the fabric of the universe into the grand structures we observe, from the smallest star clusters to the vast cosmic web. It is the hidden force that shapes the visible, allowing the light to gather and form the brilliant patterns we admire. And as the universe expands, it is not merely coasting along from the initial push of the Big Bang. No, it is accelerating, stretching outward at an ever-increasing pace, as if a quiet, unseen hand is gently but firmly pushing it apart. This mysterious force, this inherent property of space itself, is what we call dark energy. It is not something we can touch or directly measure. Rather, it is inferred from the grand, overarching movements of the cosmos. Imagine a vast, infinitely stretching fabric, and this dark energy is the subtle tension within the fabric, causing it to billow and expand. pulling distant galaxies further and further away from each other, like silent ships drifting apart on an endless darkening sea. Together, dark matter and dark energy represent the overwhelming majority of our universe's mass and energy, nearly 95% of everything that exists. We are, in a profound sense, living in a cosmos where the known is dwarfed by the unknown, where the light we see is but a thin, luminous veneer over an ocean of unseen forces. This profound mystery is not a source of fear, but of immense wonder. It is a quiet reminder of how much there is yet to learn, how much more there is to explore in the soft, dark corners of existence. You are cradled within this vast, mostly unseen universe, a small warmth held by forces we are only just beginning to grasp, drifting gently in a cosmos that holds secrets more profound than we can yet imagine. And so, we find ourselves at the edge of the known, gazing out into the shimmering horizons of scientific possibility, carried forward by the gentle current of human curiosity. Our journey through the atomic world has brought us from the earliest philosophical whispers to the most profound cosmic questions, from the minuscule dance of electrons to the sweeping expansion of galaxies. But the story of the atom, like the universe itself, is one of perpetual discovery, an endless unfolding of secrets. One of the most captivating frontiers in this unfolding narrative is the realm of quantum computing. Imagine a conventional computer which holds information as bits, either a 0 or a 1, a definitive state. Now, imagine a quantum bit, a qubit, which can exist not just as a 0 or a 1, but as both simultaneously, in a kind of gentle, probabilistic superposition. It is as if a tiny, unseen light can be both on and off at the same time, or spinning both clockwise and counterclockwise, until we gently observe it. This uncanny ability of quantum particles to exist in multiple states at once, and to be subtly entangled with each other across vast distances, forms the basis of quantum computing. These machines are not just faster, they promise a fundamentally different way of processing information, capable of quietly exploring countless possibilities at once, a symphony of simultaneous calculations. They could unlock the mysteries of complex molecules, leading to new medicines, or simulate the intricate dance of subatomic particles, helping us peer deeper into the very nature of reality, all with a quiet hum of unseen power. And then, there is the grandest quest of all, a dream that has captivated the minds of physicists for generations, the search for a theory of everything. Imagine if all the fundamental forces of nature thinned, the gentle embrace of gravity that pulls galaxies together, the subtle electric force that binds atoms, and the fierce nuclear forces that hold their cores ID, could be described by a single, elegant framework, a unified equation that harmonizes the entire cosmos. It is the dream of finding a single, beautiful melody that explains every note in the universe's grand symphony, from the quietest vibration of a quark to the most distant, echoing light of a nebula. This dream, famously pursued by Einstein and still sought today, is an attempt to see the universe not as a collection of disparate phenomena, but as a single, coherent, perfectly balanced work of art. Our journey through these unseen truths, from the ancient guesses of philosophers to the quantum whispers of tomorrow, brings us full circle. Every atom, every particle, every fundamental force contributes to the grand tapestry in which you are woven. The iron in your blood, a distant echo of a star's fiery death. The oxygen you breathe, a gift from ancient stellar explosions. The very atoms that compose your quiet, resting body trace their lineage back to the earliest moments of creation, to a universe that was younger, wilder, and still learning to become what it is. And you are floating within it, a small warmth in the dark, resting in the spiral arm of a quiet, radiant sea. The universe, in its vastness, holds you gently. Its mysteries are your mysteries. Its fundamental particles are the very stuff of your being. May this understanding bring you a profound sense of peace and belonging. I hope you sleep well and dream softly, wrapped in the quiet wonder of the atomic world. Good night.